We are now receiving a steady stream of full-color images from the James Webb Space Telescope, JWST, one of humanity's greatest technological marvels, a machine designed to peer deep into the cosmos with precision never before imagined. With its unparalleled sensitivity and resolution, the JWST has given astronomers the power to observe celestial objects with exceptional clarity, revealing parts of a universe previously hidden from view. From ancient galaxies formed just a few 100 million years after the Big Bang, to atmospheric compositions of exoplanets dozens of light years away, the JWST has become a sentinel of discovery. Among its most recent and astonishing achievements is the observation of a massive event involving Neptune, the farthest of our solar system's 8 planets. The telescope captured something extraordinary. A colossal object collided with the ice giant, sending ripples through the scientific community and raising new questions about Neptune, the outer solar system, and the dynamics still at play. In the distant corners of our celestial neighborhood, Neptune, named after the Roman god of the sea, has long fascinated astronomers with its vivid blue hue and turbulent atmosphere. It orbits the Sun at an astonishing distance of approximately 4.5 billion km, making it a frigid and remote world, one largely shrouded in mystery. But studied before, particularly during the Voyager 2 flyby in 1989, our understanding of Neptune has been limited by distance and technology. But with the power of the JWST, we've entered a new era of exploration, an age where the violent and dynamic processes of such a distant world can be seen with unprecedented detail. Neptune's supersonic winds reaching up to 2,000 kilometers per hour, its massive rotating storms, and faint ring system have always intrigued scientists. But this latest discovery, a violent collision with it massive object, has opened up entirely new avenues of inquiry into the planet's behavior and the forces still acting upon it. The event was first noticed when astronomers analyzing JWST data detected an unusual anomaly in Neptune's outer atmosphere, a sudden burst of heat and energy that appeared without precedent. Initially puzzling, the anomaly quickly gained context when the telescope's powerful imaging systems revealed a telltale bright flash in the infrared spectrum. This gigantic object, likely a large asteroid, a massive comet, or possibly even a rogue planet, had slammed into Neptune. The impact generated a massive shock wave that propagated through Neptune's dense gaseous layers, causing visible thermal disturbances and a brief but striking flash detectable from millions of kilometers away. The object size remains uncertain, but initial estimates suggest it may have been several kilometers in diameter, comparable to some of the largest known asteroids or the icy nuclei of long-period comets. Such a collision is exceptionally rare, particularly in the outer solar system. The distant and relatively stable orbital region around Neptune is not as chaotic as the inner solar system, where gravitational perturbations often hurl debris into planetary paths. This makes the impact all the more significant and mysterious. It may suggest that Neptune's gravity successfully attracted a wandering object from the Kuiper Belt, or even further from the distant and still theoretical Lord Cloud, a vast spherical shell of icy bodies believed to encase the solar system. Alternatively, the object could have been a rogue planet, a free-floating planetary body ejected from its home system and drifting through interstellar space until a fateful encounter with Neptune's immense gravitational well. Throughout Earth's own history, planetary-scale impacts have dramatically shaped geological and biological evolution. none more famous than the asteroid impact believed to have led to the extinction of the dinosaurs 66 million years ago. Jupiter, too, has been struck most notably by fragments of comet Shoemaker-Levy 9 in 1994, an event that dramatically demonstrated the solar system's continued dynamism. But for Neptune, which lies at the edge of the Sun's dominion and is seldom affected by such cosmic violence, this collision is unprecedented in modern astronomical records. The implications are manifold. For one, the massive release of energy has likely altered Neptune's atmosphere, composed predominantly of hydrogen, helium, and the shockwave would have vaporized vast quantities of gas at the impact site, generating turbulent atmospheric responses that could last for years, perhaps even decades. The infusion of energy could intensify Neptune's already extreme weather patterns, potentially giving rise to new storm systems or altering existing ones. The impact may also have had an effect on Neptune's faint ring system. The prominent and well-structured rings of Saturn. Neptune's rings are made of dust and tiny particles, barely visible and poorly understood. The force of the impact may have ejected new material into orbit or perturbed existing ring particles, changing their structure and behavior. Such alterations, if observed over time, could offer scientists valuable insights into how ring systems form, evolve, and respond to sudden disruptions. Knowledge that could be extrapolated to other planets with rings, including Uranus, Saturn, and even Jupiter. Even more intriguingly, the collision may have triggered geological or cryovolcanic activity on Neptune's largest moon, Triton, which orbits Neptune in a retrograde motion, a rare phenomenon among large moons, is believed to be a captured object from the Kuiper Belt. It is one of the most geologically active moons in the solar system, featuring geysers that spew nitrogen gas and icy particles into space. An impact of this magnitude on Neptune might have sent seismic shock waves through the system, potentially causing shifts within Triton's interior and activating increased cryovolcanic eruptions. If observed, such changes could provide unprecedented insight into the moon's subsurface composition, internal heat sources, and potential for harboring a subsurface ocean, one of the critical conditions for extraterrestrial habitability. Could there be more large objects on eccentric or unstable orbits? If this event is part of a pattern, rather than a one-time occurrence, it might signify a need to reassess the gravitational dynamics of the region and even consider the potential threat such wandering bodies could pose to inner planets, including Earth. The JWST's role in this discovery cannot be overstated. Launched in December 2021 as the successor to the Hubble Space Telescope, it has already delivered revolutionary science. Its ability to observe infrared wavelengths with incredible sensitivity makes it ideal for monitoring dynamic events in cold, distant regions of the solar system. Catching this collision in real time demonstrates not only its observational prowess but also its potential to reveal the ever-changing nature of planetary environments. This event will likely be the subject of years of follow-up observation. Scientists will monitor Neptune for atmospheric changes, modifications to its rings, and any detectable activity on its moons, especially Triton. The implications stretch beyond Neptune. Understanding how gas giants respond to massive impacts can help scientists interpret data from exoplanets, especially those that show evidence of atmospheric turbulence or unusual thermal patterns. Neptune's response to this impact could serve as a comparative model for evaluating similar phenomena on planets orbiting other stars. Furthermore, the event could reignite interest in a dedicated Neptune orbiter mission. Spacecraft has visited Neptune since Voyager 2, and a new mission could gather data on its internal structure, magnetic field, atmospheric composition, and the behavior of its moons and rings, particularly in the wake of this recent collision. Some researchers even propose sending a lander to Triton, where a subsurface ocean might exist beneath a thick icy crust. If Triton's internal heat has increased due to the energy released by the Neptune impact, ocean, if present, might become more dynamic, improving chances of detecting life-supporting chemistry or even microbial life. Studying Triton's geological responses could also refine our understanding of captured moons, objects formed elsewhere that were gravitationally ensnared by a larger planet. How such moons interact with their new hosts could shed light on the processes that shaped not just our solar system but planetary systems across the galaxy. The JWST's observation of this collision is a profound milestone that opens new windows into Neptune's mysteries while challenging long-held assumptions about the solar system's outer edge. This dramatic event, hidden in plain sight for Ian, is a reminder that even in the cold, dim corners of space, the universe is alive with sudden, transformative events. As the data continues to pour in from the James Webb Space Telescope, scientists find themselves on the cusp of unraveling some of the most elusive secrets held by the distant gas giant Neptune and its surrounding environment. This collision, a cataclysmic event observed with incredible clarity, represents far more than just a random impact in a remote corner of our solar system. There's a living laboratory offering scientists a rare chance to witness the physics of high-energy planetary events, atmospheric chemistry under extreme conditions, and perhaps most intriguingly, the possible consequences on the orbiting moon Triton. The aftershocks of this collision are not limited to the visible thermal signatures or the dynamic restructuring of Neptune's atmosphere. The implications touch nearly every major area of planetary science, extending to our models of solar system formation, the movement of small bodies, the origin of moons, and even the potential for life in places we least expected. One of the most compelling aspects of this discovery lies in what it might reveal about Neptune's internal structure, because it is a gas giant composed mainly of hydrogen, helium, and ices. Neptune's interior has remained largely theoretical, only glimpsed through remote sensing and gravitational measurements, but with shock waves from the collision rippling through its layers, scientists now have the opportunity to observe how energy propagates through its body, analyzing how long it takes the thermal signature to dissipate or migrate across the planet. Researchers can make inferences about density variations, temperature gradients, and the possible presence of a solid or semi-solid core. Just as earthquakes help geologists map Earth's interior, this planetary-scale seismic event could provide an unplanned, yet invaluable look into Neptune's mysterious heart. In addition to these internal revelations, the event also enables scientists to better understand the evolution of planetary atmospheres. After major impacts, the heat generated by such a colossal impact doesn't merely dissipate, it triggers chemical reactions, alters weather systems, and can cause long-lasting disruptions. Methane, a key component in Neptune's upper atmosphere, could undergo photochemical changes when exposed to the intense heat and ultraviolet radiation from the sun in the wake of such a collision. This could produce new hydrocarbon compounds or aerosols, potentially changing the spectral signature of the planet's atmosphere. Monitoring these changes over time may allow scientists to link spectral observations to real-time chemical processes, a skill that is crucial when studying the atmospheres of exoplanets many light years away. The implications for planetary ring systems are just as Neptune's rings, although faint and thin, are complex and not well understood. The force from the impact may have disturbed the orbits of particles within the rings or even injected new debris into the system, effectively reshaping their structure. If the rings grow brighter or more diffuse in coming months or years, this could offer clues about how ring systems evolve, how stable they are, and what role external forces play in shaping. Observing these dynamics in Neptune's rings also helps refine our understanding of similar processes that occur in the more visible ring systems of Saturn or the narrower arcs of Uranus. Triton, perhaps the most fascinating player in this unfolding drama, remains a tantalizing mystery. With its retrograde orbit and captured status, Triton is believed to be a former Kuiper Belt object that found itself gravitationally ensnared by Neptune. Unlike most moons which formed in tandem with their planets, Triton's unique trajectory makes it more of a cosmic immigrant. The collision on Neptune may have disrupted Triton's orbital stability or altered internal pressures, triggering increased geological activity. If such events can initiate or intensify cryogenic eruptions on Triton, then the energy of external impacts may play a larger role in shaping the moons of the outer solar system than previously assumed. Moreover, Triton is increasingly being viewed as a serious candidate in the search for extraterrestrial life. The surface, a crust of frozen nitrogen, conceals hints of internal warmth, and the potential for a subsurface ocean makes it comparable to moons like Europa and Enceladus, both of which are considered top astrobiological targets. The energy injected into Neptune's system by the collision might subtly warm Triton's subsurface, possibly stirring chemical processes in its hypothesized ocean that could support microbial life. The origin of the impacting object is just as tantalizing. If it came from the Oort cloud, this would be the first known instance of such a distant body making contact with a major planet, a historic milestone for solar system science. Debris from the collision might contain material from the early solar system, preserved for billions of years in the frozen depths of space. If a rogue planet were responsible, this event could represent one of the first known interactions between a planetary mass object from interstellar space and a member of our solar system. Rogue planets are believed to be common across the galaxy, formed during the early chaotic periods of planetary system evolution and flung into the void. Their potential to influence star systems they pass through is poorly understood, and this impact could help scientists better model such interactions, providing data that will reshape our understanding of interstellar dynamics. Future missions could capitalize on this event by monitoring for surface changes or geyser activity, both of which could indicate heightened internal dynamics. Back on Earth, the discovery has ignited not only scientific excitement, but also philosophical reflection. For decades, Neptune has been an overlooked world, known more for its distance than for any major revelations. But this collision reminds us that no part of the solar system is truly static. Events of immense power and consequence can occur, even in places that seem cold, distant, and unchanging. These kinds of planetary scale disruptions challenge our assumptions about the solar system's long-term stability and highlight the necessity of vigilance in studying planetary defense strategies, not just for Earth, but for understanding the broader dynamics of how solar systems evolve and potentially destabilize. Indeed, the concept of rogue planets, lonely wanderers untethered from any star, adds yet another layer of intrigue. The object that struck Neptune was one of these elusive interstellar bodies. It would provide the first direct evidence of such an entity interacting with a solar system planet. Rogue planets, by their nature, are invisible in traditional astronomical surveys, detectable only through gravitational microlensing or infrared imaging. Their interactions with structured planetary systems are almost entirely theoretical. This impact could change that, offering a glimpse into how rogue planets might influence planetary orbits, destabilize moons, or inject energy into otherwise quiet systems. Such a scenario has ramifications that go far beyond Neptune. It could reshape the very framework by which we understand planetary evolution in all star systems. The JWST's role in capturing this event speaks to its transformative power in observational astronomy. Unlike its predecessor Hubble, the JWST operates primarily in the infrared spectrum, making it ideal for detecting heat signatures from distant cold regions of space. Its ability to catch a dynamic and relatively brief event like a planetary collision on Neptune over 4 billion km away is a testament to its precision and value. As scientists continue to study the data from this event, we may find ourselves rewriting textbooks not only about Neptune but about the mechanisms of planetary change and resilience across the solar system.